let's start with speaker diarization. Speaker diarization is one more task like speaker verification and speaker identification. So first we will try to understand what speaker diarization is. Then we will see in detail two techniques to perform speaker diarization. One is X vector based diarization and the other one is a end-to-end technique for diarization. There are many methods to do diarization, but we will just focus on these two techniques for performing the task of speaker diarization. Okay. Let's move on to what is speaker diarization. Let's say you have some audio with you, okay, this audio. And this green thing is non-speech, which means some noise, okay. Non-speech. Some noise, it can be fan noise, okay, some train noise, who knows, it can be any noise, okay. And then you have two speakers in this audio, speaker A and speaker B, and in some places there is overlap, which usually happens when two people talk, right? People do not wait for the first person to finish off what they want to say. Even before that, the second person will start talking. So there are some overlaps. So there are two speakers in this audio and there is one overlap in this audio. Two noise regions or non-speech regions. Okay. Now the job of a speaker diarization system is to first split the data or split the audio corresponding to the two speakers, okay. So we have two speakers in this audio, speaker A and speaker B. So the speaker diarization system should give you two outputs, one corresponding to what speaker A spoke and one corresponding to what speaker B spoke, okay. So you see that it can split the whole audio into two different audios. And you have some noise and overlaps that will be like discarded, but in not in all cases the overlap is discarded. In end-to-end you can handle it better. So we will see how overlaps are handled better in end-to-end based techniques, okay. So this is speaker diarization. So when two speakers speak, you feed that data to a speaker diarization system and it gives out what speaker A spoke and what speaker B spoke. It's splitting the audio into two corresponding to each speaker. So the first technique to perform speaker diarization, as mentioned before, is to use X vectors. X vectors were introduced when we discussed about speaker verification. There were many other vectors discussed together with X vectors. So I had already mentioned that in the concluding remarks of speaker verification, where we will see the application of speaker verification in speaker diarization. So this is where it is going to be applied, okay. So you take the X vectors and perform speaker diarization. So to perform this speaker diarization with X vectors, you have to follow some steps, right? Okay. The first step is speech activity detection. So in the first intro slide, I showed you that there were some noise or non-speech frames and then some speech, okay, and then again some noise. So what the speech activity detection is going to do, it's just going to get the regions where speech is present, okay, it will discard non-speech. That's your speech activity detection, and then you will perform segmentation, which is that you will cut the audio into some equal length segments, okay, and then you will perform the X vector extraction process, and then you do something called a pairwise scoring, and then a clustering algorithm, agglomerative hierarchical clustering, and after you have done the clustering, you have to decide where you should stop the clustering process to get the information about the data pertaining to that particular set of speakers. So first let us see what's speech activity detection in detail, how it is done, okay. So as mentioned before, your speech activity detection or voice activity detection is going to get you the information or the regions where only speech is present. So here S is nothing but the region where speech is present, N is the region where it is non-speech. So, your voice activity detector, what it does is, it figures out the speech regions. You see this yellow square kind of wave, right, square or rectangle kind of wave. So, it performs this voice activity detection and detects the regions where speech is present and noise is present or non-speech is present. How it is done? It uses the signal energy. There is something called a short term energy. So, the short term energy is computed, and when that short term energy is higher, then you take that as a speech waveform, and if it is lower, you consider that it is a noise waveform. So, after you have performed your voice activity detector detection, you get the regions of actual speech. Okay. After speech activity detection, the next step is segmentation, right? Okay. So, once the SAD is done, that is speech activity detection is done, you have to split that audio into equal width segments. Usually the segment length is 1.5 seconds long, or it might even depend on the data that you are going to use. Okay. And some overlap is also allowed. So, how the overlap is taken is that, if my audio is this is my audio after SAD, SAD, okay, after SAD, these are going to be equal length segments, right, which are 1.5 seconds long. Similarly, this and this segment, okay. Now, if I need, so there are 5 segments in this audio. Now, if I allow overlap, what's going to happen? This is my 1.5 second long video audio S1. Because I am going to allow overlap, the second segment starts from the starts halfway through the S1 and it goes till this region. So, this is another 1.5 seconds, this is S2 and then S3, S4, S5, S6 and it goes on. Okay. So, once your segments are ready, we have to extract the X vectors. So, for this you have the trained X vector model. You just have to feed this segments, and for each segment, so segments are going to be some frames long, right? It will be some t cross 1. Here it is 1.5 second. Okay, that 1.5 second audio, you do some feature extraction. Okay, feature extraction. And you get some t cross 1, not 1, I am sorry, t cross d, I would say, t frames of d dimensions. Similarly, your segment 2 is going to be of this dimension t cross t. This will be fed and you will get a 512, it depends, okay. If you want a 512 vector, then you have to train the model for 512. If you want a 256 dimension vector, you train the model for 256 dimension, okay, or some 256 dimension vector, okay, all are that. So, you have n x vectors for n segments. Now, you can play with different vectors, it is not necessary that it should be x vectors alone, okay. Next, what you are supposed to do is a pairwise scoring. So, you had n segments, we received n x vectors from the our trained x vector model, right. Now, you have to generate pairs. How many pairs can I generate? Because it is a combination problem, it is going to be n c 2, okay. So, I have just given a pictorial representation. So, to generate pairs, you will take x vector 1 and you will pair it with x vector 2, x vector 3, goes on till x vector n, and you will take x vector 2 and again do pairings. Similarly, finally, your x vector n is paired with 1, 2 until n minus 1. So, once these pairs are generated, you will generate a PLDA score, right. This is what we did in speaker verification. We took the embeddings for a given trial pair and then you generated some scores with PLDA, where PLDA is one of the techniques to generate the scores, okay. So you generate the PLDA scores and keep it with you. We will move on to the next step. Once we have our PLDA scores, we are going to perform some clustering on top of the scores. There are different clustering methods, but we will just discuss agglomerative hierarchical clustering. So what you will do is, you will take the scores for each pair, right? You have the scores for every pair of X vectors with you. This X here marks the X vectors. Okay. So you will find the nearest pair, in the sense the one with highest PLDA score. Okay. Let us say X1 and X2 have a highest PLDA score, meaning that they are closer. Okay. So you will merge, you will say that X1 and X2 belongs to same speaker. That is the first step. So this actually means X1 and X2 belongs to same speaker. Okay, this is assumption. Okay, and it's also seen that X4 and X5 are also closer. Okay, but not as close as X1 and X2, but they are still closer. So in the second step, you will combine X4 and X5 and say that this segment S4 and S5 belongs to the same speaker. Okay, X4 and X5, which actually means segment S4 and S5 belongs to same speaker. Okay. But we still don't know whether these two are same speakers. We know that S1 and S2 belongs to same speaker, S4 and S5 belongs to same speaker, but we are not sure whether S1 and S2 and S4 and S5 belongs to the same speaker. They may belong to the same speaker, or it might be different speakers. We don't know until we perform all these clustering and then put a threshold somewhere. Okay. In the next step, let us say your X4, X5 scores are a bit closer to X3. Okay. This 5 is supposed to be here. Okay. So you merge X3 and say that S3 is closer to S4 and S5, and then finally there should be a point where you will converge and say that okay, all are like similar, right? So in the fourth step, all segments are merged together. Okay. Once this merging is done, what are we supposed to do with this merging? Okay, I have done some clustering. Okay, what do I infer from this? Okay, so if I say that this is the point that I want to like kind of put a threshold and say that okay, here I'll not merge these two sets, okay, but rather keep them as two different sets. Okay. In that case, what would this mean is S1 and S2 belongs to some speaker. Okay. S3, S4, S5 belongs to some other speaker. This is the meaning, because these two are not merged. No, I have just cut it here, right here, right? I am not allowing this clustering to happen. Okay. So this is the inference. Okay. Why should I cut the cluster diagram here? Okay. I can even cut here. No? I would have made a cut here, and then I am just saying okay. In this case, this would mean this is speaker 1, this is speaker 2, and this is speaker 3. Okay. Okay. So how do we decide where to cut? So it depends. It comes with analyzing the data and seeing like okay, where exactly should I cut to minimize the diarization errors, and then people might take a decision. Or in other cases, you know prior, okay, how many speakers are present in the data or in an audio. If we are sure that every audio is a 2-speaker kind of data, then I know that okay, I should end with 2 endpoints, right? So accordingly, I'll just put a cut in the clustering, the final clustering. Okay. So this is how speaker diarization is done with X vectors and clustering process. Okay. Let's just skip this slide. Okay. So there are few problems with this clustering based techniques. Okay. One is speaker overlap. If you see in the figure, this S1 and S2 can be speaker 1 only. This S3 can be some speaker S2 only. S4 and S5 can be speaker 3 only. There is no way S4 can belong to speaker 3 and speaker 2. Okay. So no overlap. We cannot do any, we cannot consider overlapping because we are using individual segments to generate individual X vectors and doing pairwise scoring, right. So every segment has a unique speaker. I cannot say that this segment has speaker A also speaking, speaker B also speaking. This is not at all possible when you are doing clustering based diarization. So that's one of the disadvantages. And the second disadvantage is it's not trained to directly minimize diarization errors. Instead, you are doing some kind of an indirect process. You are doing some, you are getting some X vectors, you are performing PLDA on pairs. Okay. Generating some scores, doing some clustering. Okay. There is nothing called a diarization error involved here. You are doing all these things with the hope that it will reduce, diarization errors, and it works. Okay. Now, to handle overlaps and to minimize diarization error, to bring a proper objective function into picture, a technique was introduced. Okay, that's your end-to-end neural diarization technique, which uses a transformer encoder. It can use any encoder, but right now it uses transformer encoder. So it can handle overlaps as mentioned before. It directly minimizes diarization errors, and a new loss function you will come across, which is called permutation-free loss. This end-to-end neural diarization technique uses transformer encoder. If the input features are of dimension, it is not t cross 1, rather it is t cross d, let us say, then the transformer encoder's output will be t cross some d dash. Okay, transformer encoder, the characteristic is if there are t input frames, there will be t output frames, right. Okay. And then you have a final linear layer and a sigmoid. If I am taking a 2 speaker scenario, then my linear layer will have 2 nodes, 2 speaker scenario, so 2 output nodes. Okay. So that's why it's 2 cross t cross 1, or I can just say 2 cross t, fine. Okay. Now what will you train it with? You have to provide some ground truth, right? Ground truth. Say this is speaker 1, this is speaker 2. In the sense, if there are t time frames in total, okay, let us say speaker 1 is speaking from t equal to 0 to t1, okay. Speaker 2 is speaking from t2 to t. Because there is a overlap, t2 is lesser than t1, okay, fine. So I can feed this as a ground truth, right, to train the model. This is my ground truth. Okay. Now how is this different from the other ground truth? ground truth 1 and this is ground truth 2. So, is this different from this ground truth or both are same? What would you say? Here I am saying speaker 1 speaks from 0 to T1, but here I am saying speaker 1 speaks from T2 to T. You know, it's interchanged. Actually, it doesn't matter, both are ground truths. Why? Because in diarization, we are not worried about identity of the speaker. Okay. Rather, what we are worried, whether they are same speaker or different speaker. This is our goal. After you have split them into different speakers, then you perform identity identification on top of that if your downstream task is dictating it, right? Okay. So, both are ground truths. So, the permutation-free loss takes care of both the ground truths. Okay. So, when there is two speaker scenario, the number of permutations is 2, right? It's 2, right? So, how is it odd? If it is an ordered thing, 1 comma 2 is different from 2 comma 1 in permutation. If it is a combination, both are same. So, if I have a 3 speaker scenario, n speaker scenario, how many permutations? NP2. I'm sorry, not NP2, NPN. Okay. So, these many permutations you are supposed to take care of. Okay. So, that ends our discussion on diarization and thank you.